This videotape will introduce you to the Data Visualizer version 2.1. In it, we will cover the software's use as both an interactive analysis tool and as a powerful animation system for complex, multidimensional, and time-dependent data sets. The Data Visualizer is a general-purpose graphics package with applications in any field where spatial data is produced. In earth science, the code is used widely in such diverse specialties as meteorology, oceanography, environmental engineering, and oil reservoir modeling. In this example, pressure distribution within an oil-bearing structure owned by Texaco is sectioned for volumetric analysis. Switching from macro to micro, the computational chemistry field is one which also produces complex spatial data such as this electron density distribution. The scale, of course, is substantially different, a fact which serves to underscore the Data Visualizer's utility as a virtual microscope for viewing many varieties of numeric information. The software also operates gracefully in simulation environments where both time and data dynamic range scales are extreme or nonlinear, such as this sequence of a latch-up or short-circuit event in a prototype semiconductor. While the Data Visualizer is demonstrably capable in many different application environments, in this video we will focus on its use in the demanding field of computational fluid dynamics. We will work with data sets of widely different sizes and gridding structures. The first is a small, single-block structured grid. It will be used to review techniques for data acquisition, general interface setup, and computational grid visualization. The second is a larger, multi-zone structured grid. With it, we will focus on the use of tools for viewing data on the two-dimensional field boundaries and within the three-dimensional flow field itself. The third example comes from an unstructured grid flow solution. It will be used to show the Data Visualizer's utility with both diverse gridding methodologies and large data sets. The Data Visualizer's user interface has been designed to optimize the efficiency of interactive three-dimensional analysis. The topmost control panel presents the package's primary functions. Each button creates its own set of menus for options such as viewport control, motion creation, data access, and tool generation. Tools are created by clicking on their name with the mouse. Each tool has its own display control, which is toggled on and off with these LED-type indicators. Input files are accessed via an assortment of network-compatible data readers. These are routines which are shipped in source code form, allowing for extension by the user to proprietary data formats or to specialized environment configurations. Data readers for many common file formats are available from Wavefront. In this first example, we will use a Plot3D reader, which is provided with the software and can be modified by the user. The menu panels being shown in operation here are generated by that reader. They allow selection of criteria such as grid subsampling, input block numbers, and initial data derivation. Once the data has been read in, the user interface automatically proceeds to center and size its various viewports, calculate and display the data's extent, and establish appropriate mouse interaction sensitivity. The data's extent is displayed by the bounding box tool. To make that tool current for editing, the user simply clicks on its name. Each tool generates its own set of configuration menus. At the lower left is the menu of options available for the current tool. At the lower right is the control menu for the current option. Here we've enabled the option for displaying the exterior surface of the computational grid. Initially, that surface is displayed in 4 separate windows. These are top, front, right orthographic views, and one perspective window. Switching to View Control, the upper right perspective window is current for editing. By placing the cursor anywhere in the 3D viewport and clicking and dragging with the mouse, the data view can be changed interactively with several degrees of freedom simultaneously. The Define Views function allows the user to change what is the default top, front, and right view of the data. This allows the Data Visualizer to present the same intuitive direct manipulation tool and view controls no matter how the data is oriented. Expanding the perspective window to occupy the entire viewport, we can now more easily optimize our vantage point on the data and return to analysis of the computational grid. The first step in that process is to select which of the scalar values derived for us by the Plot3D reader we want to evaluate first. In this case, pressure is chosen. A similar selection of a vector quantity can be made as well. Mesh boundary is the current option. As indicated by the menuing system, it's displayed as a wireframe surface. The first modification we'll make to that display is a switch to remove hidden lines. Cycling through some of the alternative configurations for the mesh boundary option yields displays such as this, only the edges of the computational grid. The same representation with numerical extent displayed on the bounding box. A shaded view of the mesh boundary minus the bounding box. A color map display of the computational grid surface. Color here is attached to the pressure distribution. Color mapping can be switched from smooth interpolation mode to abandoned mode. The computational grid can be displayed over the pressure map surface, or contour lines in pressure can be displayed over a shaded representation. For any of these displays, a switch to the view control mode allows for interactive positioning and inspection. Grid visualization options can of course be invoked in combination. Here, grid edges are displayed along with color pressure contours. A transparent display mode is available for all shaded tools. The mesh boundary surface display can also be controlled according to data range. By using this color slider, we can input threshold values which determine minimum and maximum data ranges for which the computational grid surface will be calculated and displayed. The color range in the slider is controlled by the Data Visualizer's Color Map Editor. We'll discuss its function a bit later on. A tool unique to the Data Visualizer is the eraser. The eraser can be thought of as both a 2D and a 3D trimming tool. It allows the user to arbitrarily cut away sections of the computational grid. Here we've enabled the 2D eraser, turned on display of the eraser icon, and initiated the first cutaway calculation. The eraser icon is represented as a red square for ease in positioning. It can be positioned either interactively or with direct keyboard entry. To maintain fluid interaction with large data sets, the Data Visualizer offers a variety of display complexity controls. This one simplifies the display of the current tool while it is being moved. Once positioning is complete, the tool is recalculated and displayed. It is this attention to functional streamlining within the interface which allows the user to steadily improve the efficiency with which production-sized datasets can be manipulated and analyzed. Eliminating display of the eraser icon, we now move towards the goal of producing a finished image or image sequence. Again, the tools required are close at hand. At the lower right of the 3D viewport are a collection of user interface control icons allowing immediate access to such functions as full screen display, black and white display, 4-view, and animation control. The Full View button expands the 3D viewport to a full screen. The black and white display option is useful for checking images which will be exported to non-color print media. The 4-view toggle button provides instant access to a means for accurately positioning tools interactively by simultaneously displaying top, front, and right orthographic views. Its utility can be seen with the eraser tool here. Finally, motion sequences can be easily created and played back with the animation control buttons. Here we've saved a start position and an end position for the eraser tool and are playing it back in full screen mode. Note that for each image displayed, the cutaway calculation is here being modified and repeated. Recall that at the outset of our work with the Mesh Boundary tool, we identified both a scalar and a vector field that we wanted to investigate. The last option we'll discuss for this tool accommodates display of vector information on the computational grid surface. As before, that display can be combined with other representations. Here it is calculated on the cutaway portion of the grid. Vectors can be displayed either in a single color or colored as a function of any of the scalar field variables available. Here pressure is used. In review then, the grid visualization tool allows the inspection of scalar and vector information on both grid exterior and interior. They can be viewed singly or in combination. As is the case with all Data Visualizer tools, they function identically, no matter what the data's gridding structure or complexity. For discussion of the next group of visualization tools and techniques, we'll switch to a different and more demanding dataset. Here our node and element count has increased by a factor of 10, and we've gone from a single block to a multi-block environment. First, the Mesh Boundary tool has been used as before to display the computational grid itself. At the interior edge of that grid is the bounding surface of interest in this analysis. The data visualizer treats that bounding surface as a geometric object. Such surfaces can be automatically extracted by the data reader, as has been done with the Plot3D reader in this example. Switching from View Control to the Tools menu, we'll take a closer look at the data visualizer's geometry visualization capabilities. As before, to make a tool current for editing, simply click on its name. Subsequently, all menu panels displayed pertain to that current tool. This includes the Move menu, where a tool's position is controlled, the Copy and Grouping menu, where tools are cloned and collected into groups, and the Data Assignment panels, where tools are attached to any of the available field variables. For the current Geometry tool, the Geometry Display option is enabled. The configuration menu for that option is shown here. One of the configuration selections for the Geometry tool allows the user to determine lighting direction. Most other options for the Geometry tool function identically to those we've just reviewed for the Mesh Boundary exploration. One exception is the ability to copy and reflect a Geometry tool around a plane of symmetry, as seen here. Other Geometry display modes focus on scalar and vector data representation and are similar to those we've seen before. The difference in the images we're seeing here is in the added annotation in the form of an axis, a color map legend, and descriptive text. These are very necessary components of a visualization system which is intended to provide both analysis and presentation graphics capabilities. Let's take a quick look at one of those annotation tools. First, we'll reduce the display overhead in the 3D viewport by turning off the legend and the pressure contour lines. Next, we'll make the text tool current for editing, in this case by simply pointing at it in the 3D viewport and clicking the middle mouse button. Our goal is to modify the on-screen text in order to introduce another visualization tool. We'll accomplish this by clicking in one of the scrollable text fields and typing the new annotation string. Text tools can be arbitrarily positioned in either the three-dimensional data environment or in the two-dimensional coordinates of the screen. The visualization tool we've just introduced with on-screen text is the isosurface. An isosurface is created in the same fashion as any other data visualizer tool. When a new tool is created, the software assigns a default name. Here we'll change that default name, creating an isosurface tool called Pressure, then attach it to the Pressure field variable. Isosurface is the current option as well. The configuration menu for this option provides a simple color bar for selecting an ISO value. With the value selected, the isosurface calculation is initiated by turning on the option's display toggle. The result is seen here. It's a surface of constant pressure at the value 0.67. Remember that tools can always be displayed in arbitrary combinations. As an example, it's a single button push to recall the pressure contour lines on the airframe fuselage. This produces a useful representation of both 2D and 3D pressure distribution. Isosurface tools can also be attached to a second scalar variable. Here we'll select density. In a similar fashion, the vector quantity velocity is chosen. Additional options for the isosurface tool include display of a vector grid on the surface and an eraser or trimming capability. Switching back to the isosurface option, we'll take a look at some of its configuration choices. First, note that both isosurfaces and isovolumes can be calculated and displayed. Coloring so far has been taken from the first scalar color map. That would be pressure. Having selected density as a second scalar, we can choose to color the isosurface using that variable's color map. Here's the result. All the usual display configurations are available. The isosurface can be displayed transparently. A color map legend can be added to define the numerical values which each color represents. The value of the legend increases when an eraser tool is used to cut away a portion of the isosurface and reveal the density values in the interior of this low-pressure vortex. Switching color control back to the first scalar yields an isosurface and cutaway section colored by pressure. Thus far, we've focused on methods for analyzing scalar data. Using techniques we've employed previously, let's move on to a tool designed for interpreting vector results. After simplifying the 3D viewport, we select the Text tool. We'll change the on-screen annotation to properly introduce this vector-oriented visualization technique. It's called the particle system. It produces both steady-state and time-dependent particle traces. In creating the particle system tool, we'll choose the name Rake, as it will be configured to duplicate a flow field analysis capability which is commonly referred to by that name. Note that the first choice for field data attachment is from the list of vector variables. We'll work with the velocity field. The particle system can also be attached to scalar information. We'll choose pressure. With the particles option current, a variety of configuration choices, such as particle count, integration technique, and release mode are available. In this example, we'll choose to launch particles in a packet from a one-dimensional emitter. The particles are leaving streamline trails, which are colored by pressure. A change of display mode removes the fuselage while the particle traces are being calculated. Line width for the traces had been increased for improved visibility. Once the calculation of the traces is complete, the display refreshes to include all currently enabled tools. Other tools, such as isosurfaces, can then be added to the display. Here the isosurface is modified to transparent to show the velocity streamlines swirling around and through this low-pressure cell. Next, we'll use this collection of flow field visualization tools to discuss operation of the data visualizer's animation functions. Simple animation setup controls are available right on the 3D viewport, as we've seen previously. A more complete set of animation options is provided from the control panel's motion menu. Here we have saved a starting position for our animation from the motion menu and switched to the views menu, where we are modifying our vantage point on the data. Reselecting the motion menu, we now save this new view as our end position. Animation will be created by allowing the computer to interpolate an arbitrary number of intermediate positions between the specified start and end. In this example, we've saved the animation as a sequence of images on disk. Switching to the Images tool on the control panel, we can display that sequence in rapid playback mode. Once the root image name and the image range has been selected, we can shuffle rapidly through those images in several different ways. The swing option plays the sequence alternating from first to last and then last to first. The loop option plays the sequence repeatedly from first to last. Finally, the frame number slider bar allows instant access to any image frame from the sequence. The motion sequence setup here is an extremely simple animation of view. Both the tools and the data were static. The keyframe techniques, however, can be as easily adapted to the animation of all Data Visualizer's tools, as well as the data itself, when that input information changes through time. Our last interactive example comes from a very different family of mesh generation and flow solvers. This is a large single-block unstructured grid solution. In its initial form, the grid consisted of over 900,000 tetrahedral elements. For this analysis, much of the far field has been stripped away using the Data Visualizer's interactive volume of interest capability, which we'll discuss further on. This has effectively reduced the data volume by 2/3 while maintaining full local resolution. The first tool we'll discuss in connection with this data is the cutting plane. The cutting plane can be used to interrogate both scalar and vector quantities. Here we've chosen pressure coefficient and velocity. The Scalar Mapping Options configuration menu contains many of the display control selections with which we've already become familiar, such as wireframe, shaded, and contour line mode. The sample and slice selections, however, are new. The cutting plane we'll show first is in sampling mode, where the user specifies a sampling resolution. The slicing plane provides a more accurate representation by performing an intersection calculation between the cut plane and the computational grid. In this mode, color display on the plane always matches the resolution of the underlying simulation. Removing the airframe from the display underscores the nature of this intersection calculation. By specifying simple display mode and enabling the Data Visualizer's computation status meter, we can get an idea of the true response time associated with interactive interrogation of this type of data set. To better bound this performance indicator, the airframe geometry contains approximately 36,000 polygons. The workstation being employed is of mid-level 3D graphics capability and contains 48 megabytes of physical memory. Display options for the cutting plane parallel those of previous tools. They include a shaded mode, a thresholding capability, plane boundary toggle, and contour line mode. Animation for the cutting plane is enabled, as in previous examples, by simply specifying a starting and ending position for the tool, along with a number of intermediate positions. The computer then interpolates those positions between the two extremes. In this example, we are playing back a motion sequence using the data visualizer's image swing option. Note the additional use of animating text to maintain accurate information on the cutting plane's position. Our next topic for discussion will be color control. Color provides one of the primary interpretable dimensions for interactive data visualization. Its control must be both flexible and efficient. Thus far, the colors used to depict scalar data distribution on all tools have come from the data visualizer's default color map. Such is the case with the scalar color display we've just drawn in the 3D viewport. By clicking on the Color Map button in the Tools menu, we gain instant access to the Color Map editor. It appears below the 3D viewport. Here it is attached to the pressure coefficient scalar data. By default, color maps express the full range of the data to which they are attached, but those ranges can be easily modified. A data histogram is provided to assist in these decisions. The tick marks below the color bar are editable. Their positions can be changed interactively, as can their color properties. Tick marks can be easily added or deleted. It is the color map tick marks that create color interpolation boundaries for the default or ramped representation of data distribution. Their position determines where contour lines are calculated and displayed. In what the user interface calls hold color map mode, they are also responsible for positioning the banding intervals seen in this data representation. The preceding interactive analysis segment dealt with a relatively large data set. It was conducted, however, on a workstation with adequate memory. To introduce the next of Data Visualizer's capabilities, let's assume that we've got a large data set to examine, but a workstation with only modest performance and memory characteristics. In this situation, the Data Visualizer offers a volume of interest tool, which allows us to interactively scale and position a sampling box within the data grid before it is actually read into memory. The data grid extent can be represented both by a simple bounding box as well as by geometry, such as the airplane fuselage seen here. To streamline this process, all of the usual display control options are applicable. Here we'll employ the 4-view mode to gain accurate positioning for a volume of interest box around just the aircraft engine and wing. Many different sampling boxes can be positioned and saved for future use in a single volume of interest session. Once the appropriate volume of interest is selected, the actual calculation is conducted by the data reader. Recall that the data reader can run on any Unix machine in our network. In a client-server mode, it will run on the host machine where the entire data set can be dealt with at one time. It will calculate the subvolume based on our volume of interest criteria and send only what has been requested back to our local workstation. From that point forward, the analysis process runs as we've seen it before. As is evident here, the volume of interest calculation excludes any element which lies even partly outside the box. In addition, the calculation works on both volume and surface data elements. The field variables read in are, of course, those present in the original data. In this example, Mach number, pressure coefficient, and velocity. For derivation of new field variables, the Data Visualizer also offers an internal data calculator. It provides for a full range of both scalar and vector operations, using simple standard mathematical and programming syntax. In this example, we will use the length operator on the velocity field to create a new scalar field called mag. It represents magnitude of the flow velocity. Frequently used formulas can be easily entered and saved for future use. The Compute button initiates the actual calculation. And the new field variable mag is added to the list of those available for analysis. The volume of interest calculation has, in this example, reduced by a factor of 13 the amount of data being accessed. In that reduced grid, however, full accuracy is maintained. For comparison purposes, this reduction in data quantity translates to a memory consumption which drops from approximately 27 megabytes to just over 8 megabytes. Note that this includes a fixed overhead for both the Data Visualizer application binary and its lookup optimization table. The last interactive inspection technique we'll review has to do with analyzing multiple variables simultaneously. In this case, we've got both pressure coefficient and Mach number to deal with. The Data Visualizer allows us to look at up to 4 such field variables simultaneously using a display control mechanism called the exclusion list, which is accessed from the Views interface. Our first move is to switch to 4-view with overall display simplified. Here we will set up somewhat differently than we've done before. Each of the 4 viewports can be assigned any of the Data Visualizer's cameras. In this case, we've assigned the perspective camera, camera 1, to all 4 viewports. Each viewport in turn has its own list of tools, the exclusion list. With that list, we can determine which tools will be displayed and which will not. Turning overall display back on yields this result. The vantage point provided by the perspective camera is duplicated in all 4 views. Each of those views, however, sees a different collection of tools. Since tools are attached to data, each can be used to represent a different property. In this case, upper right depicts Mach number both on the bounding geometry and in the surrounding flow field. Surface mesh wireframe is overlaid as well. The upper left viewport duplicates this collection of tools, but the tools are attached instead to pressure coefficient. In the bottom right and left views, no off-body data is displayed and the surface mesh wireframe is deleted. At this point, we've touched on many of the tools and techniques provided by the data visualizer for interactive data analysis. We've also learned how animation sequences are created. We'll conclude by viewing the results of linking several of these animation sequences together for a finished video production. The software used to produce these final video sequences is Wavefront's Entry Video Composer. It provides a very simple point-and-click interface approach to such functions as dissolving between images, fading from or to images, and outputting image sequences. It also provides both user interface and software drivers for controlling many popular video devices. The animation and tool control techniques should be familiar. Here, for example, we are animating the position of an isosurface eraser tool at the same time that particle streamlines are being calculated. To conclude this sequence, we merely modify our view of the data exactly as we did during the interactive portion of this video. The same view modification approach is initially used here with the unstructured grid data. That is followed by a sequence of still images of the bounding surface data display. The dissolves between these images were created in the Video Composer. The transition to display of off-boundary field data incorporates removal of the reflected geometry and a slow zoom. Now the copy tool function comes into play. At each of these transitions, a copy is made of the moving cutting plane. The animation then continues with the new copy. As copies inherit all attributes of their source, this process is simple. The last cross dissolve is to a still frame where the scalar color option has been enabled for the fuselage geometry object. Our final sequence depicts the calculation of streamlines in the large unstructured grid dataset. Streamlines are colored as a function of pressure coefficient and displayed with enhanced width to increase their visibility in video. Next, we focus in, both with our view and by employing the volume of interest function to concentrate on the complex flow field surrounding the jet engine inlet and its support pylon. Both view and particle system can be animated simultaneously. The gridding structure around and within the engine is shown, and pressure distribution both on the boundary and in the flow field is displayed. The last sequence is a change of view with all tools combined. This concludes our tour of the Data Visualizer version 2.1, an interactive data analysis software product which offers the state-of-the-art in three-dimensional exploration tools and animation capabilities. For more information on how the Data Visualizer can be applied to your complex data analysis, visualization, and presentation graphics problems, call Wavefront Technologies.